Good morning, all of you, and let's try this integral. And it feels very beautiful because you can see tan inverse something, and of course, 1 plus something is square. And that motivates me for derivative of tan inverse Golu, and its derivative is gonna be 1 by 1 plus Golu square. Okay, so with this motivation, we can start the problem. Possibly one of the way to start is to handle the second expression because maybe someone can start handling 1 to 2. So thought process TP is x minus 1 whole cube by 1 plus x minus 1 whole square. And the first motivation is to make a substitution of x minus 1 equals u because it's appearing everywhere in the problem. And that makes our problem from 0 to 1 u cube by 1 plus u square du. And since we know like u cube can be written as u square into u du, which is a usual trick of integration, that motivates me to put possibly u square as some other variable t, and that gets converted to 0 to 1, and that substitution is legal because it's 1 1 in this interval, right? So it's 0 to 1, and we'll have t dt over 1 plus t, right? Because u du is going to manage and half of that. And now this definitely can be written as t plus 1 minus 1 dt, and we can separate this integral and handle this independently. In a similar way, the first guy can be handled because tan inverse can be written as third order of y, and that's 0 to 1 dy. And we can make a substitution y equal to again v cube, and that transports this integral from 0 to 1. Remember, y equal to v cube is legal substitution because 0 to 1 is still 1 1. Okay, so when you make a substitution, make sure it's a bijection. It's 1 1, right? So 0 to 1, it's gonna give me tan inverse b to b square times 3b. And this can be possibly handled with integration by parts. So that is one motivation to come with a solution of this, but I'm not going to do that. What I'm going to do is a newer way of looking at this problem. Okay, so let's say method 2, in which I literally do almost no calculation. And the obvious presence of x minus 1 motivates me to make a substitution, and that converts the problem to third root of tan inverse of third root of u du plus 0 to 1 u cube dq by 1 plus u square. And now it's no wonder, I can see like 1 plus u square is having some tan connection because 1 plus tan square theta is secant square theta, and that motivates me to make an angle substitution of u as tan theta, which converts the second part of this integral from 0 to pi over 4. It's tan cube theta, du is secant square theta d theta over secant square theta, and that gets killed in the process, and the given integral can be written as tan inverse of third root of u du plus 0 to pi over 4 tan cube theta d theta. Now, of course, whether it's u or theta, they are dummy variables, so it's good to see with our eyes and to hear. I'll convert everything in terms of a variable x because it looks cool. So it's 0 to pi over 4 tan cube x dx. So far so good. I need to evaluate this integral. And you can notice from here that if I consider this as a function f of x, clearly f I am defining from 0 to 1, and here like to r, and r is codomain, and the range is going to be 0 to tan inverse 1, which is pi over 4. So this quantity will be certainly f inverse of x. That can be seen easily. Let's say y is tan inverse cube root of x. So it shows tan y is cube root of x, and which gives x equals tan cube of y. So roughly, if I try to plot this picture of tan inverse cube root of x, so its derivative is going to give me 1 by 1 plus x to the power 1 by 3 whole square into 1 by 3 into 1 by x to the power 2 by 3, which is strictly positive. It means the function is strictly increasing. So at 0 to 1 we are going to get pi by 4. The function behaves something like this. So this is the graph of f inverse x, and basically this represents the area which is shown there in the color. What about 0 to pi by 4? integration of 10 qx. So you know, if this is a function f of x, its reflection about a line y equal to x is going to give me the curve, right? So at 1 we are getting pi over 4. So this will be the f inverse x, and the in point is going to be pi by 4 will get 1, and 0 is still as 0. Now what is basically the integration? If I integrate this with respect to x-axis 0 to pi by 4, I'm gonna get this area, right? So let me use different color. So this is f inverse x will give this area with respect to x-axis. And that's basically same, because the area bounded by f inverse x with x-axis is same as area bounded by fx with y-axis, because you can clearly rotate this by 90 degree. So what I'm telling is, let's say if we have this function f of x, and geometrically this is representing the area bounded by the function, which is first part 0 to 1 integral f x dx. So we have this function f of x. So the second integral is nothing but simply it represents area which is bounded by f of x with y-axis. It basically represents this area, because these two areas must be exactly equal, or a definition of inverse function. And now it's no wonder, we can clearly see what is the area of this entire rectangle. At 1 we are having pi by 4, so the base is 1 and height is pi by 4. The area of rectangle is pi by 4 into 1, and that's the answer for this problem, because what we are adding is the area by the function f and plus area by the inverse function, and area by function plus area by inverse function goes to the area of rectangle, and hence the answer for this beautiful problem is pi by 4. You must have noticed like how nicely we have like manipulated these questions and converted this into a geometrical problem. Actually, you can try to next problem by yourself. So it's 0 to 1 to the power root x. Let's say we have ln squared 2 and plus ln square 1 plus x dx. So in the similar fashion, x by x plus 1 dx. And the answer that you are going to get over is ln 2, and this is left as an exercise for you. Okay, if you get the answer, keep this in the comment section so that it will help others to keep this. So both of these functions is basically based on the fact that a to b f of x dx plus f of a to f of b f inverse x dx is going to be product of upper wala minus product of the things written down. And this again a very beautiful geometrical proof, I have told. From a to b it represents this area, and the inverse function area from a to b will be same as the area by the function with respect to y-axis. So clearly you can see that geometrically the big rectangle is b times f of b minus the small rectangle will take away is a times f of a, and that proves this result geometrically. You can use integration by parts as well, assuming f is a differentiable function, because in integration by parts you'll get a term like f dash x, so you need to find this derivative. But without differentiable also, the continuity of the function is enough to prove this result, right? Of course, like you can use Riemann sums also to prove this in a very rigorous way. So I hope you have enjoyed this lecture. Stay tuned to my channel for more quality content for today. Thank you. Have a good day.